Hi, everyone. Maybe you know this famous English saying, don't judge a book by its cover. Well, my advice to you is do not judge an audiobook by its cover. Because an audiobook may be all it takes to steal your Amazon account, and I'm going to show you why in this talk. A few words about me. I'm a security researcher at Thallium, which is part of Thales Group based in France. I like anything vulnerability research, reverse engineering, exploitation, and some of my previous work includes speaking at conferences about bugs I found in Windows and Steam, and I also participated a couple of times in Pono. So, Amazon's Kindle is probably the most popular e-reader on the market. It's been around since 2007, and there are millions of ebooks on the Kindle store, so there's a quite large ecosystem around it. And so why was I interested in the security of Kindle devices? Well, a few years ago, I won a Kindle from a CTF, and something that struck me is that this device that's been sitting on my bedside table for years is connected to the internet. It's constantly running because the battery lasts very long, and it has access to my Amazon account. It can even buy books from the store with my credit card in a single click. So the security impact for bugs is real. Once an attacker got a foothold inside your Kindle, they could access personal data, steal credit card information, pivot to your local network, or even to other devices that are registered with your Amazon account. The attack surface is quite interesting. The Kindle supports many file formats that will be parsed. Of course, ebooks, there are many ebook file formats already, but also embedded media files such as images, fonts, etc., with some proprietary formats as well. There's even also an integrated browser and internal services that may be reached from within a web page. And there are several attack scenarios that one can think of. Of course, some obvious ones like local attacks or wireless attacks or even visiting a web page. But the one that I find most interesting is having a malicious ebook published on the Kindle store, because basically anyone can self-publish a book and distribute it to the Kindle store, and you could reach a lot of potential victims there with a simple download. So I'm going to start with a quick state of the art in both jailbreaking and vulnerability research. There's a quite large modding community around Kindle devices, as many users are interested in customization, and this involves jailbreaking. So in the last 10, 15 years, there's been a lot going around in the Kindle jailbreaking scene, and especially this year, there's been a lot of traction around it. And for us, jailbreaking is important to do security research because it allows to test the live system's behavior and even debug it in case we find a bug and we try to exploit it. One of the most recent software jailbreaks that was released 10 months ago is called Winterbreak, and about 2 months ago, another one called AdBreak was published. It's basically a browser exploit. And older models before, I believe, around generation 10, were jailbreakable through a serial port. You can still access this port on a recent model, but they disabled the root login. And there is, perhaps surprisingly, much less public work on actual non-jailbreak vulnerability research. Of course, jailbreaking often leverages and exploits bugs, but they're not always security bugs that have an actual impact, for instance, in a remote scenario. There's basically only 2 previous works on remote bugs. Both were in 2021 and both targeted ebooks. The first one, Kindle Drip, was basically a bug in a JPEG XR parser that is reachable through the web browser. And the second one was a bug inside the PDF parser based on libfoxit, and it was found through fuzzing by emulating a shared library. And I'd like to mention that in both cases, the exploitation part was easier because there was no SLR, there was no NX, but now, a few years later, the security of Kindle devices has improved and there are more mitigations. Now, let's talk about the Kindle software architecture. Kindle OS is based on Linux. The architecture is ARM32, and the firmware can be downloaded online from Amazon's website for all the different models, which is quite convenient. And thanks to the modding community, there are tools such as Kindle tool to extract the root file system. There's not a lot of hardening on the system, although, as I said, the security has improved over the last years. A lot of binaries still lack basic mitigations, and the libc is ancient. It's version 2.20 that was released more than 10 years ago. There's also not much access control or segmentation between processes and services. And there's basically two users. There's root, and there's a slightly less privileged one called framework, but framework can still already access sensitive data such as Amazon session cookies. Now let's look at the software architecture of the Kindle. So at the top, in blue, we have the UI components. On the one hand, a lot of the UI is built on top of an abstraction called booklets in Java. Actually, I think that recently some of the UI tends to be replaced with React Native as well. And these booklets can reach native libraries through the JNI layer. And native libraries are responsible for underlying operations such as parsing files. But the UI also relies a lot on the WebKit browser engine, which renders various HTML components. And this is done through another abstraction layer called Mesquite, which is a web application framework. And there are several Mesquite applications. For instance, you have the Kindle store, but also the integrated browser, which is itself based on Chromium. So basically, the Kindle's web browser runs Chromium inside an UI written in HTML, JS, that is itself rendered by WebKit, which is kind of funny. And these Mesquite applications have access to a native bridge through a JS object in order to reach lower level components. And this native bridge is called Pillow. In both cases, applications and system services talk to each other using LIPC, which is Amazon's own IPC library based on dbus. And it's important to note that the integrated browser, the one that runs Chromium with web pages that are potentially controlled by an attacker, does not have access to the native bridge directly. Only the JS that runs in the context of the browser's UI has access to it. But if we somehow manage to access this native bridge, we could talk to privileged system services using LIPC and Escalate. And this is basically the idea behind Winter Break. A little more detail about LIPC. LIPC services expose properties that can be read or written. There are three types of properties. There's integers, strings, and hash arrays, which are essentially a list of key-value maps. And actually, properties is a very confusing name because they are sometimes used to perform actions. For instance, here we have the Wi-Fi service with a few write-only properties that trigger actions such as connect or disconnect. And in a similar way, hash array properties are often leveraged for remote procedure calls since they take key value parameters as input and they can output a key value response as well. We can dump the whole LIPC surface on the system using a command called LIPC prob. This is very useful if we want to look for local privilege escalation vectors, and even more so knowing that there's no apparent built-in access control inside LIPC itself. So services have to roll out their own access control, and obviously they don't, which means that an unprivileged user can basically talk to any LIPC service. Therefore, if we want to achieve full chain remote code execution, one of the possible paths is to gain the ability to query LIPC services, which can be done either directly through code execution as the framework user, or by being able to run JS inside a Mesquite application, which can access the native bridge. And then we can conclude by exploiting a vulnerability inside an LIPC service that's running as root. Okay, so now let's see what happens to ebooks when they are downloaded, which is helpful if we are interested in the malicious ebook scenario. So first of all, ebooks are downloaded to the MNT US documents folder on the Kindle, and there's a component called the scanner whose role is to periodically scan this folder to detect new books. And the MNT US folder is actually a user space file system that is also exposed through USB when you connect a Kindle to a computer, so that users may also sideload books via this USB connection. And when a new book is detected, it is forwarded to an extractor depending on the file extension. There are several extractors. They're not all listed here. There's PDF, YJ, Audible, and those are usually native libraries. And the role of the extractor is to extract metadata from the book. So authors, number of pages, language, cover image, and all of this information will be added to the library, which is basically a database. And so at this point, our book can now be seen in the library and we can open it. And when we do, it goes, again, depending on the file type, through a specific reader component. So you will have the PDF reader, the YJ reader, the HTML reader, etc., which are usually implemented in Java. And so there's essentially two main phases that are interesting to look for bugs. There's the extraction phase, where there's already a first parsing of the file to fetch metadata, and the reading phase, where the book gets fully parsed and rendered. Okay, so as I said in the beginning, an audiobook is enough for a Kindle to get hacked, and this is due to a vulnerability that I found in the Audible extractor, and more specifically a heap overflow, which is what we're going to talk about now. So I was studying the scanner component and the extraction phase, and I noticed that in addition to regular ebook files, Audible files could also be loaded by Kindle. Audible is Amazon's audiobook platform, and you can actually pair Bluetooth headphones to your device and listen to audiobooks in some models, although I don't think a lot of people really use this or even know that this exists. Audible files have a specific file extension called AAX. One thing that's noteworthy is that these AAX files are processed by the scanner even if you don't own them, DRM-wise, and even if your Kindle cannot play audio. And the extractor actually goes quite deep in the parsing to fetch metadata, which makes it a really good surface. The extractor depends on a library called libaudibleaxsdk.so, which contains all the parsing logic for AX files. And there's a function exported by this library called fetch content information, and it takes a path to an AX file as argument, which makes it a good fuzzing target. So what I did is I first tried my luck by fuzzing this function with AFL++ and QEMU, but it wasn't very effective. Even after many hours of parallel fuzzing, nothing was found, and the fuzzer struggled to find new paths and exploring the parser in its entirety. It was also quite difficult to find public samples of AX files to use as input corpus, and there are very large files as well, which makes fuzzing really slow. And then I realized why it wasn't very effective, and that's because AX files are based on the MPG4 standard. So basically like an MP4 file, but with only audio and a few custom additions. It's based on a format called the ISO Base Media File Format, or ISO BMFF. Actually, a lot of multimedia file formats are based on this ISO BMFF standard, which consists of a tree structure with boxes that are also called atoms. And each atom has a name called a 4CC, 4-character code, a size, and data. The format is not very complex in itself, but there's a vast amount of atom types, more than 100 just in ISO BMFF. And this doesn't take into account atoms that are added on top of the specification. For example, there's even more atoms in MP4 and even more in AAX. So what they did here is that they basically built a whole custom MP4 parser in C from scratch, which is obviously interesting for vulnerability research. So I ended up discovering the following bug by manually reversing and reviewing the decompiled code of the library. A secret trick I like to use is exporting the whole pseudocode in IDA with Control F5 and just randomly grabbing around for weak coding patterns. It may sound like it shouldn't work, but it actually does for a lot of targets. And I quickly got an interesting hit. At some point, the extractor looks for an atom called STSC, which is used to store a table that maps samples to chunks. And there's a big endian D word that is read from the file, which I called n entries. And so we entirely control this value. And then this value is multiplied by 12 because it's used to allocate the table. And since the multiplication is performed on 32 bits, we can easily trigger an integer overflow. So for instance, with this big size here, when multiplied by 12, it will wrap around to 8, and so it would actually allocate a very small buffer of 8 bytes. And then there's a loop that iterates on the number of entries that were specified, and for each entry, it reads 3 controlled D words from our file, and it writes them to the allocated buffer. So there's an obvious textbook heap overflow here that was induced by this integer overflow. Now the question is, how can we trigger this integer overflow, and is it even reachable in the first place? Because maybe there's a check before that we haven't seen yet to make sure that the size is not too big. So thankfully, there is a code path that leads to this bug, and basically what happens is during the extraction phase, one of the last pieces of metadata that will be fetched from the AX file is a list of images that are embedded in the audiobook. And so it will first fetch the image count, and then it will call AX get image info on each image to get some info. And so we need to have a non-zero image count here to pass. And this function eventually calls another one called getFrame info mpg4, and this is where the vulnerable code lives. So to reach this bug, basically inside an MP4 tree, you have different tracks for video and audio, and there's an atom at the very bottom here called STSD, which is a table that stores information about samples. And in our case, we need to specify that a certain sample is a JPEG image. So I started from a sample AX file that I found online, and I added a JPEG entry to this atom path. Apparently, this is related to a feature that was initially developed by Apple called Enhanced Podcasts, in which you can have images for chapter thumbnails to be rendered along the audio. And so at first, I tried to use FFmpeg to edit the file and some other tools, but they don't support the AX format, although it's very close to MP4. So instead, I turned to a Python library called PyMP4. I made some adjustments to it. I added a few definitions to support some non-standard elements. Notably, some atoms were different than in the specification, and strings were handled differently as well. And then I could basically locate the STSD atom programmatically from the right track in the file and add a new JPEG entry like this. And finally, the bug can be triggered by manually patching an STSC atom that already exists in the sample file to contain a bucket size such as this one. And this is enough to make the scanner process crash because the whole heap was overwritten with garbage. Okay, so now we want to turn this heap overflow primitive into code execution. One-shot parsers are always tough to deal with because our payload, in this case the AX file, is read in one go, and we don't have any kind of response from the remote target. Either the exploit is successful or it crashes. And on top of that, it's practically impossible to have an address leak, and there's ASLR as well, so we'll need to find a way to get around it. But the first obstacle that we face here is that the write loop will basically go on forever, since it will count up to the huge integer we passed, unless there's a crash or an early exit, for instance, with these return here. But before going any further, what we should do first is try to trigger the bug on the live target to see exactly where it crashes and if there's maybe, who knows, a favorable exploitation context. So what I observed is that when triggering the bug with a QEMU user emulation setup, the process always crashed because it reached the end of the heap. But on a real device, the reality was much different. The context is different, the environment is different, the mappings, the heap activity are different, and in the end, it turns out that the shape of the heap is actually much more favorable. On the real device, the crash happened in the middle of the loop inside the function that reads the D words from the file. And more specifically, it crashed because it failed to dereference the vtable pointer for a certain object, istdio input stream, during the call to the virtual method OAA read, which purpose is to read 4 bytes from the file stream. So what happened here is that with our heap overflow, we managed to overwrite a vtable pointer, but luckily we haven't hijacked just any vtable pointer. We managed to overflow on the istdio input stream object itself. So the exploitation suddenly becomes very favorable because if we overwrite this vtable pointer, then right after on the next loop iteration, this v-table pointer is used to call the OAA read method. And so if we can craft a fake v-table with an arbitrary function pointer inside and predict its address, then we should be able to redirect the control flow literally while the heap is rewriting itself, which is quite nice. I also observed experimentally that the offset in the file at which we start overwriting the v-table pointer is usually not too far from the STSC atom. And although there's a little bit of heap non-determinism that can change this offset a little, it's still quite easy to hit reliably without having to resort to spraying. Now, the hard part, as you may have guessed, is predicting the address of a controlled buffer for the v-table overwrite, especially because of ASLR. It seems impossible to turn such an indirect call primitive into reliable arbitrary code execution in one shot and without any leak. But ultimately, we are dealing with an ARM32 target, so entropy is a bit weak in certain parts of the virtual address space, and especially in the mmap region, which is where all the shared libraries are loaded and where the big allocations fall into. So in order to find an address to data we control, the technique I used is to leverage a huge allocation. What happens is that when the size of an allocation exceeds a certain constant called default mmap threshold, glibc will call mmap instead of using the main heap arena. And this will place the allocated chunk near the shared libraries and thus reduce the entropy of its address. And we can store our fake v-table there, for example. And so we need to find a nice allocation primitive in which we control both size and contents. And I found such a primitive during the parsing of a certain metadata in the file, which is used to store the cover image for the audiobook. The contents of this cover image are read into an allocated buffer by AAX get metadata, and they do make sure that the cover is a valid image, but we can easily append arbitrary data at the end of a valid JPEG file, and we can control the size of the allocation. So we can put a huge JPEG inside this cover atom here that we can reach through this path, and at the time of the crash, we can check through proc maps that our cover was effectively memory mapped on top of all the shared libraries. Now, in order to hijack the control flow with almost perfect reliability, what I did is I sprayed the fake v-table across several megabytes of pages inside the cover image allocation. So let's say that we choose to target the fake v-table at some index g, somewhere in the middle, for instance here, which address I decide to call VG. And let's assume that we have overwritten the v-table pointer here with this address VG. This is the address that we chose to hardcode in our file and that we control. And we want to redirect the control flow to a shellcode that we put here in green, that we put right after the JPEG. Then the address of the target method in the fake v-table, which I called MG, must be defined as VG minus the distance to the shellcode by climbing up all the pages. And if we want to be able to jump on our shellcode, no matter which fake v-table we landed on, we have to extend this definition to all the target methods MK for each v-table. And this basically describes how to fill each v-table that we spray in our file, and therefore what we should put inside the cover data. And using this approach, I was able to hit the shellcode very reliably, regardless of ASLR, with around 1,000 pages of fake v-tables. Now, obviously, a big issue here is that the shellcode is not executable. Initially, I wrote the exploit for an older Kindle model from 2019, this Kindle Kids edition here, on which all allocations were RWX, so this approach was enough. And the exploit was very stable, but on more modern Kindles, we're going to have to find another way. So the idea is to perform a ROP chain, and for that we need a job gadget. Specifically, a stack pivot gadget that will make the SP register point to data we control so that we can then do a ROP chain. Stack pivot gadgets are a bit hard to find, and on top of that, context is very important. We need some kind of lucky setup in which, for instance, one of the registers at the moment of the call already points to some kind of controlled data. And luckily, at the moment of the indirect call, it happens that the R8 register actually points to the start of the buffer that was just allocated. So the one that was subject to the heap overflow where we have controlled data. So now what we can do is try to find a gadget that will pivot the stack to the R8 register specifically. This one had me stuck for some time. I tried to use the usual tools like RobGadget against all the libraries that are loaded inside the process, but I couldn't find anything useful until I found this one magic trick that's documented nowhere online. Basically, the ARM instruction set consists of 4-byte instructions, but you can switch to another mode called the thumb mode by jumping to an address with the LSB set to 1. And this mode relies on an instruction set extension called thumb2, in which instructions are mixed, so they are either 2 bytes or 4 bytes, which means that 4-byte instructions can even be misaligned, so to speak. And so there's a higher code density, which naturally also means that there will be more gadgets. So it's important to search through thumb2 gadgets as well to get more candidates. So when decoding instructions as thumb2, we can find this quite powerful LDM gadget. What the LDM instruction does is it pops a whole set of registers relatively from where the source register points to in memory. And I found the perfect gadget inside libsqlite. This one will set all the registers according to the data which R8 points to. And so by jumping to this gadget address +1, we can switch to thumb mode and we can control all these registers and specifically the SP and PC registers, which is very nice. Interestingly, as I said, tools like RobGadget did not output these gadgets even when specifying thumb mode. So I made a pull request to add these LDM patterns for job gadgets, which has been merged in RobGadget 7.6. And even more interestingly, according to the ARM v7a specification, LDM instructions in thumb mode have to follow certain rules, namely that SP cannot be in the register list and PC and LR cannot be both in the register list at the same time. So these gadgets are not even supposed to be valid instructions according to the specification. And yet they still somehow run on the Kindle's Cortex A7 CPU, which is very convenient for us. Anyway, so now we are able to run an arbitrary ROP chain in the context of the scanner process, and this is enough to conclude the exploit. So we can summarize it like this. In step 1, we have our heap overflow in which we overwrite the target object, istdio input stream. Then in step 2, we overwrite the vtable pointer with a hypothetical address that will very likely point to one of our fake vtables inside the huge memory mapped cover image that we made sure is allocated before all of this happens. Then in step 3, we are able to redirect the control flow. So we jump on this LDM job gadget. Then in step 4, we are able to control the SP and PC registers, so we can do a stack pivot. And what we did here is that we sprayed ROP chains along each fake vtable so that we know that we can pivot there. And finally, in step 5, we execute the ROP chain, in which I decided to use a CSU gadget in the scanner binary itself, which gives a controlled function call. And I use it to call mprotect to make the shellcode RWX and eventually jump on it. So the biggest issue with this exploit is that the address of the job gadget needs to be hard-coded. Its entropy is approximately 9 bits, and combined with the fact that the heap overflow sometimes fails because the heap layout is not fully deterministic, I estimate the exploit to hit with around a 1 in 1,000 chance. This may seem low, but this low success rate actually works in a real exploitation scenario, and that is because after a crash, the scanner process automatically restarts and parses the file again. So we can make an hypothesis on the gadget's address, and we can just wait until we reach a configuration where the address is correct. And all of this happens in the background for as long as needed without the victim ever noticing, because the scanner process is silent when it crashes. Sometimes it takes a whole minute to restart, which can make the exploitation a little slow, up to several hours, but this is still fine for an attacker because the exploit runs silently in the background, and Kindle e-readers are usually able to stay powered on for many days thanks to their battery. So in the end, the impact is still there. Once we are able to run a shellcode, we can run a second stage script as the framework user. From there, as I said in the beginning, we can basically already steal crucial Amazon session cookies, which are located in the cookie jar file used in the Mesquite store application. And this is enough to take over the victim's Amazon account. But let's try going further. We don't have full control of the Kindle yet, so can we find a privilege escalation to become root? The second vulnerability I will talk about is a local privilege escalation in the keyboard service. So my first intuition when looking for a local privilege escalation was to turn to LIPC services running as root. As we said earlier, there are many LIPC services, and it's a surface that has already been exploited in the past, for instance, in the recent winter break and ad break jailbreaks, so it feels natural to look there. My attention was caught by a service called lab126 keyboard, which is exposed by the KB process running as root. And it seems that the service acts as an interface to the on-screen keyboard so that other processes can make the keyboard appear on the screen, change its configuration, make it disappear, etc. And in particular, you can supply a list of languages separated by colons through this writable property here, and then you can change the keyboard's language. So I analyzed the library responsible for this service, which is libkb.so. And to be honest, from there, finding an LP was only a matter of minutes. I looked at the setter handler for the languages property, which is the code that handles when you write to the property. And what happens is that each language that we supply is validated by checking if this path here exists. So basically, if there's a key map file associated with this language. And immediately, there's an obvious path traversal bug here that we can leverage to point to a control key map outside of the user share keyboard folder. So if we set the languages property to something like this here, the path will resolve to somewhere in the MNT-US folder, which as the framework user, we have the permission to write to. And so we can create a fake key map file in this folder, and then our language identifier will be deemed valid. And well, now that we successfully added a new language to the list, we can load it using the language property without S this time. And it turns out that the setter handler for the language property actually suffers from the exact same path traversal problem. But even better this time, the result path is supposed to be a shared library that's going to be loaded with DL open. And so we can load an arbitrary shared library here, which basically gives free code execution as root. Exploiting this bug is quite straightforward because there are built-in LIPC command line utilities on the system to read and write properties, so everything fits in a single bash script. And finally, the shared library can be leveraged to execute a third stage payload, such as connecting to reverse shell or running post-jailbreak logic if we are interested in jailbreaking. Okay, so we have the full chain. Now let's watch a video demonstration of the proof of concept. So first, I have to mention that I chose to emulate the attack vector by dropping a malicious audiobook to the Kindle via USB. In a real exploitation scenario, the book may be downloaded by the victim from online. So I send the book to the Kindle through this USB connection. And then I have to disconnect the USB for the changes to actually take effect on the file system. And as we can see, arbitrary code is executed as root. And we can show some arbitrary stuff on the screen. We can also see that we are able to retrieve the Amazon session token. Of course, if you listened carefully earlier, I said that the exploit was not entirely reliable and that it could take hours to land successfully by running in the background. So for this video specifically, I cheated just a little bit with ASLR so that it works on the first try. Now, if we want to go even further, as the attacker, we can actually steal the whole cookie jar that is stored in the victim's device. So we can see here that I've received the victim's cookie jar on my computer, and then I can go to Amazon's website. So as we can see, we are not currently logged in. And then I will use this Firefox extension to import the victim's cookie jar into my browser, reload the page, and now we're logged in as the victim. A few words to end this presentation. So we achieved remote code execution on a Kindle through a chain of vulnerabilities triggered by a malicious audiobook. We used this to demonstrate an Amazon account takeover, but this chain could technically also be used for jailbreak. I reported the bugs in January through Amazon's HackerOne bug bounty program. The Audible bug was fixed in March, and the keyboard service bug was fixed in September. Amazon assessed both bugs to be high severity, but they also acknowledged that when the two bugs were chained together, they reached critical, so the reward was $20,000, which we decided to donate to a charity. So what do we take away from all of this? First, impact. Some devices that we use every day might seem harmless, but can actually hide a large surface and valuable assets for an attacker, so you definitely don't want your Kindle to get hacked. And if you do vulnerability research, maybe this can inspire you to find new targets. The surfaces in which we found bugs are also present in other applications or devices, like the AAX library, which is reused in Audible apps on many platforms, like desktop and mobile apps, or the LIPC library, which can be found in other Amazon products, such as the Amazon Echo. So be mindful of that when you're looking at attack surfaces, because this really multiplies the impact. In terms of vulnerability research, we saw that in complex parsers, generic fuzzing may not always be very effective, especially in multimedia parsers where seeds can get very large. One thing you can do is develop a custom mutator, but what we did here instead was that we leveraged a bottom-up approach by directly looking for vulnerable patterns in the code base. So you don't always need heavy tooling to have results. Don't forget your basics. And finally, as far as the exploitation goes, we observed that one-shot parsers are difficult to address. Here, a few elements made life easier, like the address space being 32-bit, and the lack of modern mitigation, such as control flow integrity or memory tagging. And even with that, we were unable to come up with a fully reliable exploit. But we also learned that depending on the scenario, unreliable exploits can still have an impact. So if you are ever exploiting a bug and you have an idea how to do it, but you're hesitant because it's a bit contrived or it's not reliable enough, and you feel like you should throw this bug away, then always remember to think about context and scenario, because sometimes there's actually a really viable impact, and you just have to shift your perspective. Thank you for coming to my talk. If anyone's got any questions, feel free to reach out to me during the conference or on my socials. And apparently you can also give some feedback using this QR code. And yeah, thank you.